morning or afternoon, depending on where you're at. Welcome to the ACPA webinar series. Today we have structural pipe design. We have two speakers, Paul M. and Riley Dvorak. Both are with Forterra Pipe and Precast. We're going to give everybody just a couple minutes to finish getting logged in. But if you are on the line, you should have a panel that gives you some options on different items. And so if you see the question pane, it's probably the most important. Everybody is in listen-only mode, so we can't hear you speak. That just helps to keep the noise down with a larger group that we have today. But if you do have questions, feel free to type those in the question pane, and we will get those answered. If they're specific to a slide that's being discussed, I'll stop the presenter and ask that. If it's a more generic question, we'll hold a lot of those till the end to make sure we have enough time, and we'll cover as many as possible at the end of the presentation. So we'll just give everybody just another minute or two to get logged in. Okay, well, to be respectful of everyone's time here, let's go ahead and get started. Again, this is the ACPA webinar series, and today we're talking about structural pipe design. And first up, we have Paul M. He's out of Canada with Forterra. So Paul, I'll turn it over to you.
Great, thank you, Kim. Yeah, as Kim mentioned, I'm with Forterra Pipe and Precast up here in Canada in the drainage division. I'm the director of engineering here, and I've been here for about 8 months now. Prior to that, I got my engineering degree in civil engineering from the University of Waterloo, and I've been a professional engineer here in Ontario since 1997. I started out in the consulting world in land development, so you know, I was doing a lot of things that I'm sure the audience is involved with still, with drainage and site servicing of land development projects. I was using DOS-based programs back then, so I think things have advanced since. And then I joined a local concrete pipe producer, spent about 11 years there as their engineering and quality manager. I then spent 10 years with the Canadian Concrete Pipe and Precast Association up here in Canada, so it gave me an opportunity to go across the country and do a lot of educational seminars like this one. And what you realize is, you know, knowing everything you need to know about pipe is challenging enough, but then, you know, you have the challenge of trying to teach other people some of this technical information, which, you know, I was able to practice when I was teaching a buried infrastructure course at George Brown College up here in Toronto. So hopefully you guys get a lot of benefit to this from this, and you know, I'm looking forward to it. So,
hey, Paul, before you jump right in, let me just mention one thing real quick. I know a lot of you guys are engineers, licensed engineers on the call, and so I just want to address PDHs. Those will be, we document who is in attendance at this meeting, and if you are in attendance, we will send you a certificate based on what you registered for this webinar with. And if you are in a group that you have multiple people on the call, if you will shoot myself an email, which you should be able to reply to the confirmations that you got. Otherwise, my email is kspawn, S-P as in Peter, A-H-N as in Nancy, at concretepipe.org. And let me know who's in your group, and that way we can make sure we get certificates to everybody. All right, thanks, Paul.
Yeah, no problem. Yeah, so as an overview today, Riley and I will cover both rigid and flexible pipe design. I'll just give you a quick overview of how the two different pipe types behave once you bury them. Then I'll proceed to cover the indirect design method with standard installation beddings that's covered in the AASHTO LRFD code. And then Riley will take over and explain the plastic pipe design method. And then we'll just summarize everything at the end. So as mentioned, the AASHTO LRFD code covers the design methods for both concrete and the flexible pipe materials. And in general, we share the same kind of design theory that basically buried pipe is a structure that becomes, it's a composite system comprised of the pipe and the soil envelope. And so in 12.10, reinforced concrete pipe is covered. And in 12.12, it covers the thermoplastics, and then it has other sections for corrugated metal and materials like that. Now for concrete pipe, it has sections that covers both the direct design method and the indirect design method. For today, we're going to cover the most commonly used design method, which is indirect design, and I'll get into that a little bit more. But just for background information, direct design is like designing any other reinforced concrete structure where you have to check a variety of failure modes, which results in a unique pipe design for just your specific project. So in my opinion, the most appropriate time to use it is when you have a special installation condition that is outside of the fill height tables that are published, and I'll talk about a little bit later, which is all based on the indirect design method. So again, you should sort of reserve the times that you use direct design for any kind of special cases, but for the most part, you're going to be using indirect design. Now, what I like to see in a lot of contracts and other standard specifications is just a reminder to the engineer of record. As Kim mentioned, many of you are probably professional engineers or are working your way towards getting your professional designation. And so you have to watch or be mindful of clauses like this. The professional engineer responsible for preparation of engineering drawings is also responsible for the structural design of pipe installations. Now, a lot of the engineers I come across are typically hydraulics experts or pavement experts. They're not necessarily structural engineers, so they're not comfortable with the structural design of pipe. But again, if you're going to put your professional seal on these plans, you are responsible for the structural component of the pipe installation as well. And some clauses will go on to say that in all cases, designers shall keep a record of structural design calculations associated with each project. Design calculations for specific projects shall be provided to the city upon request. So again, it's just a reminder to especially professional engineers that there is a standard of care that you have to be mindful of. I guess this is a good prompt for a poll question, Kim.
Okay, great, thanks, Paul. So I'm going to launch a polling question that you guys will be able to answer on screen. So this question is, when are you required to submit structural design calculations for drainage pipe? Is it when you're designing concrete pipe only, plastic pipe only, both concrete and plastic pipe? Never, you don't have to submit structural design calculations, or not sure? So this goes back to what Paul's talking about, actually designing the structure and the soil. Give everybody just a couple minutes to enter their answer there. Okay, I'm going to close that. Paul, since you can't see it, you got 13% for concrete pipe only, 1% for plastic pipe only, 58% for concrete and plastic, 11% never, and 17% is I'm not sure.
Okay. Great. Well, I guess it's encouraging that 58% require design calculations for both, but I guess it's obvious there's room for improvement there, that 11 don't ever have to do calculations, or 17 are not sure. So it's good. I guess there's some people will have to do some digging in their local areas. Now, just to give you a brief overview of how rigid and flexible pipe behave, the best explanation I ever saw was in a textbook called Buried Pipe Design by A.P. Moser, where he uses the analogy of soil springs to explain how rigid and flexible pipe behave differently. Now, in the case of a rigid pipe, as I show you here in the left-hand side, you can represent the pipe as a rigid spring or a stiff spring, because it's not going to compress or deflect very much. And then the side soil on either side of the pipe can be represented with flexible springs, because relative to the pipe, that side soil is a little bit more compressible. So when you load these three springs from above with your typical live load and earth load, what ends up happening is the side soil is a little bit more compressible than the middle column, represented with the stiff spring there. And so what also happens when this occurs is you get this frictional force, or this down drag, where the pipe in the center column is not only carrying the load from directly above it, but it's also carrying some of the load from either side of it, because of that, because of the fact that the side soil is a little bit more compressible. Now, when you look at the plastic pipe side, you situate the springs in the exact opposite scenario. So obviously a flexible pipe is going to compress a little bit more or easier than the side soil. And it's not a defect in the pipe, that's just the way flexible pipe is designed to work. It's designed to transfer the load into the soil. It's really not designed to carry much load. So again, in this scenario on the right-hand side, you would represent the middle column with a flexible spring and the side soil as rigid springs. And when you load those three springs, the same thing occurs, except it's in the opposite situation here, where the middle column is a little bit more compressible than the two side columns. And what also ends up happening then is you get a frictional force in the upward direction, where the side soil actually reduces some of the load on the pipe. So again, that's the flexible pipe theory versus the concrete pipe theory. And this friction force is what's called the vertical arching factor. So in the case of a rigid pipe on the right-hand side, the vertical arching factor has a value greater than 1, which is a mathematical way of saying it's not only carrying the soil above it, but it's also carrying some of the soil from either side of it. And in the flexible pipe scenario, the vertical arching factor is typically less than 1, which is a way of representing how the pipe is not even carrying the load above it, because the side soil is removing or taking some of that load away from the pipe. So again, that's a very fundamental difference in how rigid and flexible pipe behaves when you bury it. Now again, obviously when you load a rigid pipe, like again I have on the left here, what ends up happening is that load gets transferred through the pipe down into the foundation or the bedding that it's sitting in. So obviously the bedding area and the haunch area up to the spring line of the pipe, the midpoint of the pipe, is what a concrete pipe design is mainly focused on. It's the lower half of the support that the concrete pipe is getting. It does rely a little bit on lateral support, but again, it's not as critical. So with concrete pipe, what it offers you is there are 4 bedding types, which I'll explain a little bit later, and 5 standard pipe classes, which allows a designer to come up with the combination that is the most economical for them in their particular situation. Now on the flexible pipe side, obviously again, the foundation that the pipe is sitting on is critically important to ensure that you don't get settlement and things like that. But imagine if this pipe was being loaded with just support on the bottom. Obviously you're going to flatten that pipe right out. So what flexible pipe also requires is this passive side soil support to control the deflection. So really, to sum that up, flexible pipe is a lot more installation sensitive, which, as Riley will explain later, results in a much more complex design method. You're not really designing the pipe, actually. You're designing the soil envelope around the pipe. And for those reasons that I just explained in the last two slides, we have very different bedding details. So on the left, I have C1479, which is the installation spec for concrete pipe. And on the right, I have D2321, which is covers the installation of plastic pipe. And you can see in this shaded area here, again, these are the critical zones or the structural backfill required around each of the types of pipe that we're going to talk about today. So again, for concrete pipe, we're very much concerned with everything below the spring line. And for flexible pipe, it's the entire soil envelope that the pipe relies on for proper performance. So really, I mean, I guess the moral of the story with this is you can't just look at the price difference between a concrete pipe and a flexible pipe. You have to look at the total cost of constructing that, because the backfill and bedding materials are also very important for both, but they're also very different. Now, as far as the evolution of concrete pipe design, back in the 1930s, Marston and Spangler came up with some design theories, and they came up with what we call traditional beddings now, class A, B, C, or D. And they also developed the indirect design method. It was very much empirical. They went out and studied a bunch of installations and did a lot of tests to develop some equations around indirect design. Obviously, the indirect design method has stood the test of time because we're still using it today. But then in the 1980s, on the right-hand side here, Frank Hager kind of redefined the pressure distribution around the pipe. So he developed the 4 types of beddings that these diagrams represent, and also and called them the standard installation beddings. So you have type 1 on the left-hand side here, which is the highest quality bedding, and then down to type 4, which is the lowest. And these beddings can actually be used for both the direct design or the indirect design method. So, and that's what we use today. So in the AASHTO code, you'll see all the reference to the type 1, 2, 3, or 4 beddings as far as concrete pipe installation goes. And you can see from this diagram here that the soil pressure in the invert, so right at the 6 o'clock position of the pipe, is increasing as your bedding quality decreases. And also the difference, the soil pressure in the haunch region also starts to change relative to the pressure at the invert, which is where you start to see, in this case over here, you get maximum bending moments. And that's why for a type 4 pipe, sorry, my laser pointer is a little glitchy, so it's distracting. For a type 4 pipe, you will need a much stronger pipe or a higher strength class of a pipe than you would for a type 1 type installation. So so that's the difference here, and these pressure diagrams are a good graphic way of seeing how the pressures are distributed around the pipe. So what the indirect design method is based on is an actual physical test of the pipe that we do at the plant. It's called the 3-edge bearing test, or often referred to as the DLoad test. The test method is covered in ASTM C497, and the criteria that we're looking for is either the 0.01 inch crack, which is what we use as the service limit, and again, we call that the DLoad, and also obviously the ultimate strength of the pipe. So those are the two main things that we're looking for with this pipe. You can see that it's only making 3 points of contact with the pipe. So this is an extremely severe loading condition. You would never see this in the field. And again, it's this 0.01 inch design crack that we use as sort of our criteria. But the thing to keep in mind is a 0.01 inch crack is just arbitrary. It doesn't mean that the pipe is being overstressed or has failed at all. It's just sort of a arbitrary value that's only meant to provide consistency in our quality control tests. So it doesn't matter which plant you're doing the test in, we're all looking for exactly the same crack width. Just to give you a frame of reference, a dime is 5 times thicker than the 0.01 inch crack that we're looking for. So you can see in this photo here, we have a very thin feeler gauge that we're using to perform this QC test. Now, if you're familiar with the ASTM standard for concrete pipe C76, there are 5 standard classes of pipe in the standard. What this chart here is, it summarizes what the DLoad of the 5 classes are and also what the ultimate load of the 5 classes are. And it's measured in units of pounds per linear foot per foot diameter. So just to give you a quick example, if somebody asked you what's the minimum load required for an 18-inch class 5 pipe in a 3-edge bearing test, the math is pretty simple. To calculate that, all you have to do is take the strength of the pipe, the pipe length, and the inside diameter of the pipe, which I've taken here because we're talking about a class 5 pipe. I would use the value of 3,000 pounds per foot, multiply that by a typical lay length of 8 feet, and the inside diameter, because it's 18 inches, it works out to 1.5 feet. You take the product of those 3 numbers and you end up with 36,000 pounds. So that's how much load an 18-inch class 5 pipe needs to carry before this 0.01 inch crack appears over a 12-inch length. And then similarly, for the ultimate strength of the pipe, you would now use the value of 3750 in the same equation and end up with 45,000 pounds. So you can see, even for a small pipe like an 18-inch pipe, it takes a significant amount of load before even this little 0.01 inch crack appears. So the load carrying capacity of the pipe is pretty significant. Now, for reinforced concrete pipe design, just to get into the weeds a little bit, again, I'll be talking about the indirect design method using standard installation beddings. So again, as a designer, you have a couple of options. You can go through the AASHTO code or the ACPA's design manual and just hand calculate everything. Obviously, this is accurate, but it's also very tedious. There is a computer software program that was recently launched as an online tool rather than a program you had to install on your PC, called PipePack. So this is the indirect design program that's available online at pipepack.com. It's obviously very efficient, but the user needs to still understand the design principles. And then finally, the simplest thing to do is to reference the fill height table. So ACPA has done all the work for you and published design tables for not only circular pipe, but for the non-circular as well, the elliptical and the arch. So if you go on their website, you can download these fill height tables. It's quick, but again, as designers, you need to understand the assumptions that was used to generate these tables, because it is possible that your situation may be too different from the assumptions used in these tables, that you shouldn't be using them at all. So as far as the indirect design overview, this equation kind of summarizes what the indirect design calculation looks like. You have to calculate or determine all the external loads on the pipe. So you have your earth load, your fluid load, and your live load. Those are the primary types of loads you're going to see in most cases. You have to decide what type of standard installation bedding are you going to specify. Determine the bedding factors based on the step above, based on the type of installation you're going to specify. Apply a factor of safety. Now, if you're designing to the 0.1 inch crack criteria, your factor of safety just becomes 1. And then once you have all that, obviously you already know what the diameter of the pipe is that you need. You calculate the DLoad that you require. And once you do that, you just round up to the nearest standard pipe class that will meet that criteria. So that pretty much sums up the indirect design process. And a good resource is ACPA's Design Data 9. They really just do a good job of walking you through the entire process in good detail with sample calculations and things like that. Now, when you're looking at a concrete pipe installation, you really you could consider 2 possible options here. You can have what's called a trench installation, where you have a very narrow excavation and you're putting the pipe inside that. And the benefit of a trench installation is you will get some frictional forces between the backfill and the trench walls that actually reduces some of the load on the pipe. So you can see these frictional forces are in the upward direction. And so the trench walls, if they're close enough to the pipe, they're actually going to reduce the load on the pipe. Now, I guess the practical side of that is it's very difficult to control trench width in the field. It's hard to know. I mean, some contractors, no matter how well intended they are, for one reason or another, they may have to open up the excavation much wider than you specify. So you have to really be mindful of that. And so then we go to the more extreme case called the embankment installation, or more specifically, the positive projection embankment. And again, this is sort of that spring analogy that I touched on early on today, where you have a great big excavation, so you don't have any trench walls to help you like you do on the trench condition. But instead, you have that drag down force, because again, the side soil is settling a little bit more than the middle soil, the middle column. So you have this drag down force. And so for design, it's always best to assume the worst case scenario and assume that it's an embankment installation. That's pretty much what we recommend probably 100% of the time out there, or almost 100% of the time. Now, when you're designing pipe, obviously you're going to wonder, well, what about the weight of the pipe itself? If you talk to your local producer, they will often use terms like, well, we have a B wall or a C wall. These are the equations for those wall types. It's just a function of its inside diameter. And they do vary from producer to between producers. So you should get some local knowledge there. For direct design, you do have to consider the weight of the pipe, the self weight of the pipe. But in indirect, you don't, because indirect is based on that 3-edge bearing test. It's an actual physical test on a full-size pipe. Obviously, the weight of the self weight of the pipe is going to affect how it performs in the test. So for that reason, we don't have to account for the weight in any of our calculations. Now, for the earth load, the simple way of looking at earth load is basically it's the prism load, the column of soil directly on top of the pipe, multiplied by the vertical arching factor. That's that drag down force from the side soil. So if you look at both AASHTO and the ACPA manual, they both provide equations to calculate the earth load, but they are slightly different. You can see here that AASHTO has really simplified their equation. They use the term FE, F sub E for the arching factor. But then what I've circled here just represents a rectangle or a column of soil directly on top of the pipe. So you just have the density of this soil times the width of the pipe on the outside and the depth, or the H. So they just treat this as a simple rectangle in their formula, but the ACPA kind of goes a little bit further. They also account for this little, I guess what I would refer to as an upper haunch area. And so their equation accounts for that small area as well. So it's a little more accurate, I guess, to be blunt about it. And for the unit weight of the soil, AASHTO has a clause that says you can't use less than 110 pounds per cubic feet. Typically in design, you're using 120. I think most texts that you reference will use that value. And then the arching factor for the 4 standard installation types, I've just summarized here. And again, they're all published in the AASHTO code or in ACPA manuals. You can see type 1, which is again the highest quality type of a bedding, which includes the side soil. So for that reason, you're not going to get as much settlement and as much drag down force. So your arching factor is 1.35. And type 4, which is the lowest quality installation, you're going to get a slightly higher arching factor of 1.45. Now the fluid load also needs to be considered. So you have to account for the weight of the water that's inside the pipe. And again, here's the AASHTO clause that tells you need to do that. It's just as simple as calculating the cross-sectional area of your pipe and multiplying it by the unit weight of water, 62.4 pounds per cubic feet. And we treat the water inside the pipe, it's being supported by the lower part of the pipe. So that's why we kind of lump it together with the earth load and use the earth load bedding factor. So that's where it sits in the equation there. Now the live load, which I show over here, typically if your installation is 8 feet deep or less, you have to account for live load. Anything deeper than that, you generally don't. It just works out to be negligible. If you have a pipe that's buried more than 8 feet deep, it's really not going to feel any of the trucks. And again, I'm referring to the truck live load. So to get some background information on the highway loads or design trucks, ACPA has a helpful publication, Design Data 1. And basically it walks you through how you look at a design truck. You have to look at a few possible combinations of the wheel loads over the pipe, which includes also 2 trucks passing each other 4 feet apart directly over the pipe, and then pick the worst case scenario out of all those combinations that you have to look at. Now there are other kinds of live loads out there. There's aircraft loads and railroad. So again, ACPA has some design data sheets to cover those as well. And those are all available for download free of charge at ACPA's website. Now finally, the bedding factor. So far we've covered everything in the numerator in the indirect design equation. Now it comes down to the critical bedding factors. Now, if you read the textbook, this is how the bedding factor is presented. It's defined as the ratio of maximum moments in the 3-edge bearing test to the maximum moment in the buried condition when the vertical loads under each condition are equal. That's kind of a quote from right out of the design manual. Now, I've read that probably 100 times and I still kind of scratch my head about it. It's a lot to digest. And so the way I like to think about it is I rearrange this equation, and in very kind of simple layman's terms, I think of it as whatever the pipe strength was during the DLoad test at the plant, the same pipe being installed in the field is stronger by a multiple of whatever the bedding factor is. That's really how I think of it in my mind. And this chart here gives you an idea what the bedding factors are for a variety of pipe sizes and for the 4 different installation types. So you can see, I think typically most specs will use a type 2 or a type 3 type installation. So you can see that you're increasing the load carrying capacity of the pipe by around 2.5 to 3 times what that same pipe could carry in that 3-edge bearing test or that DLoad test. So that's really how the bedding factors work relative to the pipe strength. And then there are also live load bedding factors that are published. So these values are straight out of the 8th edition of the LRFD. But one thing to keep in mind is they changed it in this edition. So if you look at any of the ACPA documents or even the 7th edition of the LRFD, you'll see slightly different live load bedding factors, but it shouldn't make a significant difference to your type 2 or 3 installation. Really, I think when it might become more significant is if you're looking at a type 4 installation. But again, I don't want to get too much into the weeds on that one. Just be aware of that, I guess. Now, finally, the easiest tool to use, obviously, are fill height tables. The ACPA's fill height tables are based on the indirect design method. It assumes a positive projecting embankment situation. So again, that's sort of the worst case scenario. It assumes a seawall for all the pipe sizes, and the only reason for that is so you can, that is the thickest wall that you can get for each size. And so by doing that, you're maximizing the earth load or the prism load on the pipe because you're using the biggest outside diameter available out there. It uses a soil weight of 120 pounds per cubic feet. The HL93 truck. And it also has accounts for a clause that's in the AASHTO code that says if you're designing with a type 1 installation, because type 1's, it's the highest quality bedding, it's also out of the 4, the most difficult to achieve. So for that reason, they wanted to throw in another sort of factor of safety in there, what they call the installation factor of 1.1. So these are the assumptions that went into the ACPA fill height tables. And again, for the majority of installations out there across the country, these should be suitable. And my final thought here is I just wanted to present a couple of examples of what the fill height tables look like. So I have a type 2 installation versus a type 3 installation just behind it here. And you can see as an example, if I looked at the range of sizes down this left-hand column, at a 14-foot depth, as an example, you can see that if I use a type 2 installation, all of my pipe, regardless of what size, ends up being a class 3 pipe. Now the same pipe being used in a type 3, which is a slightly lower quality bedding, the result changes. You can see a lot of the sizes change to a class 4 pipe just from the color difference. So the values you see in the table is the actual deload that's calculated, and then they round up to the nearest standard pipe strength. And you can see just from the colors that the majority go up one size one strength class. So it's good as a designer to be aware of this and where those thresholds are, because you may want to tell your field people that look, if the contractor cuts some corners and doesn't give you a true type 2 installation, you may be in trouble. Or as a designer, you may want to specify a class 4 just so you know that even if the installation isn't as per spec, you're not going to have a structural problem. So as designers, you kind of need to look at things from that perspective. And so that concludes the concrete pipe section.
Okay,
Kim?
Great. Thanks, Paul. I think we had one more poll we wanted to launch.
Oh, did I miss that?
Let me throw that out there, and then you can comment on the results. Okay, so this one is, what structural design tool do you use for concrete pipe? Paul went over a couple of different options. In your jurisdiction, do you use fill height tables? Do you use the software that Paul showed us, PipePack? Do you require direct design for concrete pipe? Do you use something different, other? Or I'm not sure. Okay, so Paul, the results are 63% use fill height tables, 10% use PipePack, 6% use direct design, 8% is other, and 14% is not sure.
Okay. I'm curious to know what the other is, but yeah, that's interesting. Well, it's good. I mean, obviously the fill height tables is the simplest, and as I mentioned, it covers the broad range of installations out there. So that's great.
Yeah, a couple of comments I had just before we move on for Riley. I'm going to switch it over to you, Riley, and then while you get set up, if anybody has any questions, again, if you want to type those into the question panel, we can get some of those answered. Great job, Paul. Appreciate your help with that. One question was, we've had a couple of people ask if the presentation will be available following this webinar. And yes, we will post the recording as well as a PDF of this presentation for you to use as your notes. So if you need anything else though beyond that, please just let me know and we can get you what you need. Another point is I will put a link. Our fill height tables are pretty easy to find under our design tab on our website, but I will also put a link to those with the recording so you guys can find those if you need them. One question was about the factor of safety. When you mentioned, Paul, that with a 0.01, use a factor of safety of 1, and why would that be? I think as engineers, we always question, how can you have a factor of safety of 1? But that's because there's still capacity within that pipe. So beyond that 0.01 inch crack, there's additional capacity to load that pipe to the ultimate load. And that's anywhere between 25 to 50% higher capacity, depending on the class of pipe. So your factor of safety is already built into that 0.01 inch crack. And then Paul, you mentioned sometimes fill heights the fill height tables shouldn't be used, and that the designer needs to know the assumptions. You went through those assumptions very well. I was just going to give an example or two of when they might not apply. And that was when you mentioned those railroad loadings or airport loadings, something beyond a highway load, because they do assume highway loading. So in those more specialized cases, that would be when you want to look at using PipePack possibly. And then if you go beyond those fill height tables of a class 5, if you need something more than a class 5, our manufacturers can actually do what Paul mentioned as a direct design and build a special product for you that will still meet the needs of those specialty loading situations. And then the only other comment I saw, questions coming in, was a type 1 installation. Paul, I think you hit that pretty good. We even have a caution note in our fill height tables about a type 1 installation. I just caution designers typically, unless there are special cases you really need a type 1 installation to meet your needs, or you have a lot of inspection. If you're going to use a type 1, I recommend that you make sure you have inspection on site, as Paul mentioned, to make sure the contractor is giving you what you designed. I kind of suggest that you stay away from type 1 because it is more difficult to achieve, and it does make that pipe more installation sensitive which I think leads perfectly into Riley's discussion on plastic pipe design. Any other comments or questions for me, Paul, before I turn it over?
No, that's pretty much it. And I guess the last thought is just don't be afraid to reach out to your local concrete pipe producer. I mean, we all have a lot of technical expertise, a lot of years of experience. I know from Forterra's perspective, you know, I'll shamelessly plug us. We have a lot of engineers on staff that can help designers in the early stages. That'll prevent a lot of problems down the road.
Great point, Paul. Okay, Riley, you're up, and we can see your screen. So
okay, Darren, you can hear me as well.
Yep.
You can hear me?
Yep, I can hear you.
Okay, good. And are we done at 1? Is that the cutoff?
Yeah, we'll try and wrap it up by 1. We'll probably take questions beyond that, but we'll let folks go if they need to go.
Okay, yeah, absolutely. I will say I've got about 50 minutes of material to get done then in about 15 minutes, which I'm a really fast talker, so I'm hoping I'm up for the challenge. I'm going to skip my introduction a little bit, but I've been just briefly. I've been with Forterra for about 6 years now. I've done a lot of different roles from estimating and drafting to sales, and now I'm a technical resource engineer for the Minnesota region. And I've spent a fair amount of time looking into plastic pipe design, mostly because I just think the more you know, the better off you are, and really I'm sure that's why a lot of you are here today. I was actually last year named the I do a lot in the ASTM world, kind of on a national level. And last year, believe it or not, was named the emerging leader or emerging professional for the representing the plastic pipe ASTM committee. So I have been very fairly involved, and so I hope to share some of that knowledge today. So this next section, we're handling plastic pipe design. And so we really don't have the time to look at each step very thoroughly. So we're just going to be covering some basic principles. When we talk about plastic pipe design, I got to figure out how to switch to the next slide here. We're looking at the AASHTO LRFD bridge design specifications. And this is by a large margin the most widely used and accepted method for plastic pipe from a structural design perspective. And there are 3 basic strength limit states that we're going to be testing to, and that's thrust, buckling, and combined strains. And then for service limit states, we also check deflection, which is a largely important indicator for just the long-term performance of the pipe. Lastly, flotation is another design consideration that needs to be checked, but the AASHTO manual doesn't specifically cover this, so we're not going to really touch on that at all today. One important fact to point out is that LRFD is going to assume, just to begin with, that the native soil is just as stiff as the backfill itself, and is going to be providing adequate vertical and lateral support with a minimum trench width. So they reference for those situations outside of that, where that assumption might not apply, they reference the AWWA manual M45, which is actually the fiberglass pipe design manual. And what they outline in there is that you know, if you run into those situations, you basically just need to increase your trench width. Sometimes up to 5 pipe diameters might be necessary if you have really weak soil. So obviously something to just be aware of right from the start. So yeah, basic design principle being that if the native soil is really weak, you need to remove more of it, replace it with a stiffer backfill in order for that plastic pipe to be able to deflect, to transfer the loads into the soil. So a question that some of you might be asking yourselves is why can't we just pull up the fill height tables that we've used before, that we've seen before? Well, and I'm just going to say that understanding the LRFD methodology is going to be really important for anyone even before they start to or attempt to use fill height tables, because every fill height table for plastic pipe is going to be built on a number of assumptions. Number one, that most of the pipes are going to be installed in direct accordance with ASTM D23. They also assume that the water table is below the pipe, so no hydrostatic pressure. And they also assume that the native soil is, again, at least as stiff as the backfill material. And the interesting thing is if we actually pull up the fill height tables that are out there for the different manufacturers, say if we, for example, pulled up a 48-inch pipe with specific class 2 backfill compacted to 95%, all the fill height tables we see, even with those common assumptions, are going to vary tremendously between manufacturers. And that's partly because there's a lot of nuances in the design assumptions, and there's different variables that in LRFD you're allowed to some leeway to, as a designer, pick a range of factors. But another huge factor in that is that each manufacturer is going to have a specific profile for their pipe wall. So these 4 examples, J-Amigo, Prinsco, Haviland, and ADS, all have their own, even with a corrugated dual wall pipe, have their own profile for their pipe wall design. That's going to vary from the next manufacturer. So we see here that because of all of those reasons, the fill heights are going to vary quite a bit. So you can be as high as 30 feet, it might be as low as 17 feet. So it's just important to recognize that just choosing one of the fill height tables and running with the values they have listed may not be appropriate for your specific situation. It might be too conservative or might be underdesigned. There's not a real way to know without completing an actual design. Both the wall geometry and the mechanical properties of plastic pipe are going to vary significantly if you're using a different pipe material or a different manufacturer who has a different wall design. The moment of inertia, the distance from the centroid of the pipe wall to the outermost element, which is an important thing to know for calculating stresses in the pipe wall, the spacing of the corrugations, and the effective pipe wall area, we'll talk about that in a little bit, they all play a pretty significant role in determining what those wall stresses are and what you end up having for estimated deflections. LRFD is going to provide initial and long-term properties of the different plastic pipe materials, so that's in a table, but it does state that there's some uncertainty in the actual values, and it suggests that designers actually ask the pipe suppliers or even maybe the resin suppliers to provide confirmation of those values for a particular pipe product. So it's important that as you approach your particular designs for plastic pipe, is you know what pipe material and profile you're using, and even if you know you're using corrugated HDPE, it's important to know the differences between manufacturers in your area. Because of this variances between pipe manufacturers in regards to pipe geometry, LRFD states in the design, the commentary to their design, that really manufacturer specific section properties need to be used for plastic pipe design because there really isn't a way that anyone can assemble one generic conservative assumption for the pipe profile that's going to cover all the components of the design in a conservative nature. For example, if you have a compact profile shape, that might give you an advantage in some of the design limit states, but there's multiple of them that you're checking, and it might hurt you in a more compact profile shape might hurt you in other areas, such as deflection. Section properties for plastic pipe really should be readily available, so it shouldn't be too hard to assemble these. The pipe manufacturer should have those ready to go. Otherwise, you can determine those from optical scans of the pipe, or there's other tests that you can run to determine that. So you'll need to be aware of that for all of the approved plastic pipe suppliers in your regions. So the first part of a plastic pipe design, now kind of getting into it, is we need to determine, just like we did for concrete pipe, what's our soil load on the pipe. For plastic pipe, this is denoted by PSP, soil prism pressure, and this is the pressure just due to the weight of the soil above the pipe, also including the unit weight for the soil above the water table. So there's kind of depending on the location of the water table, the calculation is going to take one of 3 forms, whether the water table is above the surface level right here, or whether it's below the top of the pipe or somewhere in between. We're going to note that soil pressure doesn't include any hydrostatic pressure. So that's a totally different calculation. That's called P sub W, PW, and that's force, kind of acting at the spring line. And that's another calculation that must be done if you have a water table that's above the spring line. If it's below that, then your water pressure is 0. I don't have a slide on that, but it is covered in LRFD, and that's going to be need to be accounted for the wall thrust calculation, which we'll look at next. Last note, again, we need to check for flotation if we do have a water table that's above the top of the pipe. Again, that's not covered in LRFD. But there's other manuals that should be able to point you in the right direction. So this leads us to our first strain-based check for plastic pipe. So what we're using is the soil prism pressure, over the top of the pipe with the groundwater pressure and the live load. So you can see in this top equation, yeah, there it is. So the soil load, this PSP, we're taking that. There's a lot of factors, so it looks confusing. Obviously, we've got that vertical arching factor in there as well that Paul talked about earlier, which is actually going to help a plastic pipe. It's actually going to pull some of the load back from the soil prism acting down on the pipe. Then we've got a groundwater pressure and our live load. So you kind of break it down into 3 different terms, obviously with a lot of factors for that, but that's really what the bones of that equation are. And since thrust can occur at various locations around the circumference of a pipe, we need to do that calculation for both the spring line of the pipe and the crown of the pipe. So this thrust, what it is basically is we're calculating the force that's going to be transferred by those loads into the wall of the pipe, and so you can imagine that force kind of going all around the circumference of the pipe and compressing those sections. So it then translates into epsilon u sub c, which is this factored compressive strain. The thrust will translate into the compressive strain by basically just dividing it by, that's just a conversion factor, and then you've got your area, your effective area of your pipe, and your pipe modulus. So that's really all you're doing, just to convert the thrust, which is a force, into a strain acting on the pipe wall. So we need to also remember that we're designing this we might be designing this for short-term or long-term properties of the pipe, because that's going to vary for plastic pipe, whether you're looking at a short-term, which includes your live loads and things like that, or if you're looking at long-term, which you're looking at more of your permanent loads, which are earth loads or permanent high groundwater tables. Yeah. So the same factored compressive strain from the previous slide, the epsilon u sub c, also needs to be checked against a different strain limit. So on the previous slide, I'll go back here, we were checking the compressive strain that we got from the thrust against just a material limit, and that's found in a table in AASHTO. There's another limit that we have to check it again, and that's just a buckling limit, similarly to like you would have with a steel beam. So there's a material strain limit, and there's also a buckling strain limit based on all of the properties of the pipe profile itself, pipe materials, and it also factors in the soil, and we'll look at that in a little bit here. So this buckling strain limit is defined as the pipe's ability to resist buckling, and it's going to depend on both the pipe properties, kind of in this term here, and the soil properties in this term here. It's also important to note here that only certain parts of that pipe wall are going to resist local buckling, and that's your area effective. And so your gross area, or your actual area of your pipe wall, is going to need to be reduced. There's ways that are outlined in LRFD that you can do that. I'm not going to really get into that, but just so you're aware, that's not the gross area of the pipe wall. You're actually going to be taking an effective section. There's only certain parts that are going to actually resist buckling. So again, we point out that soil is just as critical, if not more critical, in these strain calculations for resisting buckling. So we're going to look at this term later on, but just note that this M sub S, which is the modulus of the soil around the pipe, that's showing up here, and it's going to show up later as well. So now that we've checked the compressive strain due to thrust and compared that against the material limits and the buckling limit, to this point, we actually haven't even factored in the strains from deflection. And so when a plastic pipe deflects, kind of shown in this diagram, it's going to create tensile and compressive strains in the pipe wall, as we see, and a net tensile strain, which we haven't really even looked at yet. That can cause, what we see in plastic pipe is the cracking or the tearing of the pipe wall. And then the compressive strain can cause yielding or buckling. So these compressive strains are going to add to that thrust value, and we're going to need to check those again against the strain limits that we looked at in those tables. So in the first design check, we see here, these are the combined strain design checks. In the first one, we see on the left side of the equation that we're taking the E sub F, which is the strain due to flexure, and we're subtracting out what we had in the previous slides as our factored compressive strain. So if we have a net tensile strain, then from that, so if we have a tensile strain, E sub F, that's greater than our compressive strain due to thrust, then we're gonna need to compare that against the tensile strain limits, which is epsilon YT with a factor in there. So we check that, make sure that we're okay there, and then we also need to then take that strain due to flexure, so our compressive strains in this deflected model, and we're adding that to the thrust strains, which are just the forces going through the pipe wall, and then we compare that again to the compressive strain limits, which is epsilon Y sub C. So those are the two checks we do there. Now, to back up a bit, in order to get these flexural strains, what we need to do is we need to calculate our estimated deflection. We need to estimate how much flexure that we're going to have, and that's caused by bending deformation. And we see this is an equation right out of AASHTO, and it looks actually similar to a modified Iowa formula that maybe some of you are familiar with for calculating flexible pipes deflection. In the numerator, we're going to have the total load, which is soil load plus live load, and then in the denominator, what's resisting deflection is the pipe stiffness plus the soil stiffness. Now, in addition then to this bending deformation, which is this term here, we also need to factor in what's called circumferential shortening, and this epsilon S of C, which is the surface compressive strain due to thrust. So before we were looking at the ultimate compressive strain due to thrust, this is the surface load, and we need to calculate that. And so basically this is circumferential shortening, which, if you can imagine, as that thrust goes through the pipe wall, that's going to basically decrease the circumference of the pipe by a certain amount, and that's going to factor into what we estimate deflection might be, because we're going to be calculating the vertical and horizontal span of the pipe. So that's going to be one of the factors. And we note here that the vertical arching factor is not used in this deflection equation, which means we're actually here, we're assuming that the maximum soil prism load is going to be acting down on the pipe, and not a reduced load that we use to calculate the thrust. So this estimated deflection needs to be checked against then a maximum allowable deflection, and AASHTO includes that the maximum deflection limit, most people will say 5% is generally appropriate for just about every plastic pipe. The actual deflection a pipe experiences is going to be controlled by proper construction in the field. So LRFD actually states in their commentary that contracts that engineers assemble need to place the responsibility for deflection control on the contractor. So to verify that the pipe was installed accurately to the assumptions used in the design, we strongly recommend using deflection measurements to verify that the proper embedment and soil structure has been established. Now, I do want to stop now briefly and talk about this M sub S term that we saw previously, which is your soil stiffness. And this term is really the most important term in designing the expected quality of a pipe installation, and it's really the biggest factor in what what your allowable fill heights are going to be for plastic pipe. And this actually replaces a more commonly known term called E prime, which is what's used in that modified Iowa formula. And this M sub S term really should be somewhat more accurate, because other than in contrast to the E prime term, it actually is going to factor in the depth of the backfill. Assuming that a deeper backfill, a deeper burial with a deeper with a higher soil prism stress level is going to cause that soil to be a little bit more compressed just naturally. So ideally, you'd be able to have a site-specific data for your S value used in the design, but to my knowledge, there's really not a way to determine that in the field, or really even the in situ soil outside of a very in-depth geotechnical survey. It's really going to be hard to come by this value. So for that reason, the LRFD manual is going to provide a simplified table shown here that can be used to determine the soil modulus using assumptions for backfill. So whether you're using sands and gravels, which is this top portion here, or silts, which is the middle portion here, or clays, which is the bottom portion here. And then you see this different compaction levels going from the left to the right. So this would be 100% compaction, 95% compaction for all three soil types, 90% for all three, and 85% for all three. And then we're looking at what your soil prism pressure is, and we're determining our M sub S value based on those three factors. So when you have soil prism stresses that are in between these values, you can interpolate, but when it comes to soil types and compaction types, it's a little more general. All soil in this table, all soils are basically put into three pretty broad categories. So if you have a mixture, it's generally not appropriate to do some kind of interpolation. Really, you want to choose the more conservative assumption, so the lesser quality. Assume that you're getting a lower quality soil and less compaction by a degree of 5%. The interpolation between compaction levels isn't necessarily appropriate either. So you really want to just assume the lower quality side, just as a measure of conservatism. Now, just to give you a flavor of how critical this M sub S term is to the design, let's run just a quick calculation of a 48-inch plastic pipe with 25 feet of fill, and we're going to compare all three soil types with 95% compaction. So using all of these assumptions into this is just the deflection equation. This isn't a full design, but just the deflection equation. This is kind of what we output if we we use the same level of compaction, but all we do is vary the soil type. And so you can see here that we're going to anticipate anywhere between 4.6% deflection for a sand and gravel, up to 13.5% deflection. So that's 3 times as much deflection just by changing the soil type. Now, if we took just that sand and gravel type of installation and we varied just then the compaction level for that soil type, what we find here is our deflection is going to vary then between 3.2% and 14.7%. So that's now we're looking at a difference of nearly 5 times as much deflection for a lightly compacted installation versus a highly compacted installation. So this isn't meant to knock on plastic pipe, but just to simply illustrate how critical the soil structure is for plastic pipe design. So not only the selection of proper assumptions is important, but also the verifications of those assumptions in the field. So here's just a graphical example of that. I'm gonna, just for sake of time, I'm just gonna skip through that. So as we mentioned previously, deflection testing is a widely used means of verifying the soil embedment of the pipe. And it's crucial to note that the timing of that deflection testing is very important. In AASHTO section 30, it states that this test for verifying the deflection requirements or deflection estimations were not exceeded really should take place no sooner than 30 days of backfill. And this is intended to give the time for the backfill above the pipe to settle initially, and hopefully at that point the pipe is seeing the highest loads it's going to experience, which are the construction loads from excavators and pavers driving overhead. Some entities are going to require deflection testing prior to final acceptance or at the end of a warranty period, which might be 1 or 2 years. Other entities might just practice routine deflection testing as part of ongoing pipe maintenance. And that last one, that might be something, that might be too costly or difficult for municipalities or people to do on a routine basis. But it could alert the users to issues before they become a major concern. So there is some value there. One last note on deflection testing is to remember that each manufacturer's pipe dimensions are different. So they have a unique inside diameter that can be more or less than the nominal diameter that was required in the design. So keep that in mind. That shouldn't need to be prior to determining what your mandrel diameter is. You need to know what manufacturer is supplying the pipe on that job, because their pipe diameters can vary plus or minus 1% of the nominal inside diameters, which might not seem as significant value, but when we're talking about a critical deflection level of 5%, that might make the difference one way or the other. Kim, let's turn it over to you. Let's just do a quick poll. I know we're already over time. I'm assuming that if people wanted to leave by now, they would have left. So we've probably got a good core group that's still with us that hopefully.
Yeah, Riley, I was going to mention to the group, we do still have quite a few folks online. So, if this goes to 12:15, 12:30, something like that, we'll adjust the PDHs that we send out to 1.25 or 1.5 PDHs. So appreciate you guys sticking with us. The next polling question I'm going to launch that you guys should be able to answer online there is, when is deflection test done for flexible pipe in your jurisdiction? Do you do it 30 days after backfill? Do you also do it before the warranty ends by itself? Do you do both of the above, both 30 days after backfill and before the warranty ends? The fourth option is we don't require deflection testing, and the fifth is I'm not sure. Okay, so Riley, your responses there is 28% say they do it 30 days after backfill. 4% do it before the warranty period ends. 12% do both 30 days and before the warranty period ends. 18% do not require deflection testing, and 38% are not sure.
So quite a mix there. No, that's it. In my region, 30 days is by far the most common. I think there's a few people that might do the warranty period. I think the 38% being not sure is actually that's the majority of people out there, and I think that's halfway expected. I think not a lot of people are aware of what those requirements are. I think there are requirements out there, but a lot of people aren't totally sure what they are. I find that a lot of times. Yeah, 12% doing both. That's I think that's a good practice. Even just for the contractor, even if you're only doing the prior to the warranty period ending, even a contractor knowing that might want to run it through at 30 days just to see where he's sitting, because it's much easier to replace that pipe sooner before you get too much going on over the top of the pipe instead of waiting to the end of the warranty period, and then you might risk having to completely tear up a new road and all the amenities overhead. But okay, awesome.
Yeah, I'd say, Riley, just to add to that is the 38, well, actually almost 50% that either don't require it or are not sure, is to think about that and talk to some of your pipe suppliers, concrete pipe suppliers, plaster pipe suppliers in your area. I think what Riley's gone over today hopefully has shared some knowledge with you of how critical that installation is. And so you guys are opening yourselves to liability by not verifying that you've gotten what you've specified. So certainly something to think about implementing if you're not currently doing that.
Okay, am I back in control now here?
Yes, we see your blank screen or your blank slide.
Awesome. Okay, so another quick note on that is this is a note from Amster Howard's work on load lag, deflection lag, and time lag, and it's an article specifically related to flexible pipe. Amster Howard's a technical expert on the subject. He spent like 30 years with the Bureau of Reclamation, and he's written several books and technical papers on these types of subject. But in a technical note, he actually states that the maximum load on a given pipe doesn't occur until 3 to 6 months after backfilling. So even that 30 days waiting period, you might not be seeing the most load that pipe experiences. So this is just kind of reiterating my point that it's important to understand the timing of when that test occurs, because plastic pipe is going to continue to deflect to some degree over its lifespan. So you want to kind of hit it at a critical point in the lifespan of that pipe, which is, some people say 30 days, but here we see that that maximum load might not hit the pipe until 3 to 6 months. So that might be one reason to wait until maybe that warranty period to run up before you pull mandrel through the lines instead of just once at the 30-day mark. So that really covers the basics of flexible pipe design. We looked at the strength limit states where we check the compressive strains due to thrust against the specific pipe material limits. We also check the buckling strains, which depend on both the pipe and soil properties. And we also check the combined strains with the added strains from deflection. And then as a service limit check, deflection is also estimated and compared against the deflection limit that needs to be verified in the field, as we mentioned. And then flotation, again, a separate consideration, not covered here today. So as we conclude, I want to do a side-by-side comparison since we covered both design processes. And this is really intended to illustrate that there are fundamental differences in design methodologies between rigid and flexible pipe, and it's important for you guys as designers to recognize these differences when you're designing a system that might include one material or the other, or potentially both. It's important to highlight what those distinctions are going to be. So the first one is that with reinforced concrete pipe, we're going to provide standard strength classes that are going to be consistent for all manufacturers. So every manufacturer is going to be on a level playing field in that regard. Paul mentioned before that wall thicknesses sometimes vary between manufacturers, but the strength requirement is still there. So regardless of what the wall thickness is, that pipe's still going to be meeting the same strength that it's required to meet. For plastic pipe, it's a little different because there are going to be different wall profiles between manufacturers, and those different wall profiles are going to largely impact your design. So multiple designs might be necessary if you're in an area where there's maybe more than one pipe manufacturer. Second, we know that there are two types of design for rigid pipe per AASHTO, and that's the indirect and direct design method. Indirect is the simplified method built on strength classes and bedding factors, and that's what makes fill height tables possible and pretty easily acceptable. Direct design is the more complex and typically used for those projects outside of the sizes and classes found in ASTM and AASHTO standards. With flexible pipe, then, we just point out that the only type of design that's allowed is direct design. And that's where each installation needs to be checked to analyze the specific stresses that pipe wall is going to experience within the material limits for that pipe. And then next, we want to point out that in a rigid pipe, the primary structure, what's primarily carrying the load, is the pipe itself. So the primary portion of your design is designing the pipe. So selecting the appropriate pipe class is really the majority of what you're doing for the design. For a flexible pipe system, the primary structure is provided by the soil. So the primary part of your design is designing the soil structure around the pipe. So that structure is tested two different ways. For a rigid pipe, it's tested in our plants, and that's where the structure is built. We use that 3-edge bearing test to verify that structure. And a flexible pipe, since the structure is built in the field, that structure also needs to be tested in the field using some means of deflection testing, whether it be mandrel or laser profile, or whatever you're doing. And then lastly, and this really isn't something we touched on today, but the expected design life of rigid pipe is between the two systems is going to be based on different things. For rigid pipe, it's going to be based on historical performance data. We've had our pipe around for quite a while. Flexible pipe, because it's a relatively new material, it's going to be just based on the known time-dependent behavior of the material properties. And I'll also mention that for rigid pipe, we have that design software that's available through the ACPA. And if any of you guys need access to that, you can find it on the website, or reach out to an industry representative. We can point you in the right direction there. So that's all we had. We really appreciate everyone sticking with us. We're 20 minutes late officially, but I do notice here that we've got a fair amount of people still on, and I really do appreciate that. I'm glad that we have interest here. Yeah, I'll hand it over to Kim, and I think we'll hopefully get a few questions in here if everyone still has some time to stick around, and if you're curious about anything, throw it out there.
Yeah, great. Thanks, Riley. Appreciate the education on that. A couple of things before we move into questions, in case some of you do have to drop off. We will adjust for those of you who did stay on. Again, the PDH is up to 1.5 PDHs if you stayed on till this point. Next thing is PDHs. If I mentioned this at the beginning, but if you hopped on a little late, if you are on with a group, if you'll send me an email with your group list and their emails, we'll add them to our certification list of attendees to make sure they get their PDH certificate. Again, this presentation and the PDF of the slides will be available on the ACPA website. I will send out a link to all of you who did attend. So that'll probably be in the next day or so. You'll see that come out. And last thing I had as housekeeping was our next webinar, kind of to follow up on what Riley finished with on deflection testing, will be in October. And that will be with Al Hogan and Jason Hewitt on inspection and evaluation of pipe once they are installed. So thank you guys for joining us. I do want to go through, we have some great questions here. Let me see. Can you arrange a tutorial for a pipe tech program? That's a great question. Yeah, we'll put that on our list for future webinars, and we possibly can walk through some pipe pack designs. So that's a great idea. We also have a design software that designs box culverts. So maybe we can couple those together in the future. It'll probably be the start of the year. We have scheduled out a couple more webinars currently, but that's a great idea. Let's see, another question, Riley, for you was, what in the deflection vary from mid-pipe to connection of a structure or another piece of pipe with flexible pipe?
So is the deflection going to vary if you have, a coupler, or if you're right at a structure?
Yeah, I believe that's what they're asking.
Yeah, no, absolutely, and that's definitely something that needs to be factored in. It's the couplers are going to have obviously a different wall profile than the pipe itself. So that might be something that needs to be evaluated. Most of the time, it's over the top of the pipe, so you're actually adding a little bit more material. So at the coupler, it's maybe not as much a concern. I know up to the structure is something that has been brought to my attention a couple of times. Is that oftentimes contractors, as well-intending as they are, might backfill under the haunch and get all the proper compaction over the pipe during the majority of the run, but oftentimes it's hard to get those compactors in close to the structure. So oftentimes what you see is some of the least compacted material around that pipe is going to be right at the structure, and so you see a lot more deflection sometimes right at the structure, the pipe structure interface than you would for or during for the rest of the run. So it's a consideration, and you know, it all comes down to you as a designer. Is you know, is that what you want to design for? Is it acceptable to have some deflection right at that that interface? And if you are, you need to, you know, then you need to look at what type of connection you're using for that structure to pipe connection. Because if you're going to anticipate that there's a lot of deflection right at that structure, you should probably be using some kind of flexible connector, either a water stopper, or we recommend using flexible rubber boots. So I hope that answers it. I guess from a design perspective, it really just comes down to you might need to use a different set of assumptions for if you're trying to control those deflections and those stresses at those different locations.
Yeah, great. Thanks, Riley. I think you make a great point. Even the plastic pipe manufacturer would recommend a rubber or flexible booted connection to their pipe because there is going to be that deflection there, that movement where the structure itself will be much more rigid. Typically, it is a concrete structure, so just be aware that when you're making those connections that you're using proper connectors. Or if you're connecting a rigid to a rigid, you can actually use a grouted connection possibly. And so there is that as a difference. Another question for you back on your soils, Riley, is the soil modulus for the soil in the soil envelope or the soil on the side of the trench? I think that they're talking about outside of that soil envelope.
So your M sub S is what you're anticipating you're going to get for your actual compacted backfill. So that's the entire soil envelope of what you put around that pipe. Now the assumption is that your trench walls are going to be at least as stiff as that. If that's not the case, then we've got you have to look at other references to know how to account for that. I think that's straightforward enough a question where that answers it. But yeah, it's really talking about the soil envelope.
Yeah, great. I think that answers what they were looking for. Another question was, do you see flexible testing, deflection testing, being done on private development projects?
Yeah, yeah, we do. A lot of times, some of those development projects are turned over to the city at the end of a certain time, and so oftentimes the cities are going to require that be included in the specifications. So that's what I see commonly for a lot of developments. I do know that sometimes we talked about that. We took that poll where a lot of people are not sure on those deflection requirements. I will say that sometimes it's in the specifications, but it's maybe not being completed. So people are maybe not as familiar with doing those for development projects, but a lot of times it actually is in the project requirements.
Here's an interesting one. Could you discuss the backfill approach when you have two pipe trench with varying materials?
Two pipes in the same trench?
I believe that's what they're asking. Two pipes in the same trench with
different
various
materials. If you have a plastic pipe installed right next to a concrete pipe?
I believe that's what they're asking.
Golly, I honestly don't know how that would be handled from a design perspective. There's probably people that have. Paul, do you have any thoughts on that? I don't have any particular experience of how those designs would be handled, because that would be kind of a mix.
Yeah, I mean, combined trenches are quite common. You have to basically just design to the lowest common denominator, whichever, obviously the plastic pipe design is going to govern. The concrete pipe is only important up to the spring line, and the concrete pipe, you have to make sure you have, if you recall that detail I showed, at least 6 inches of cover over the plastic pipe. So that's going to be what governs typically.
Yeah, and then the other thing is just to make sure you have enough room to get compaction between those two pipe materials.
Right.
That would be sufficient enough for that plastic pipe.
And actually, I referred to the Moser book, the buried pipe design textbook, and they cover a lot of different scenarios like that, where you have to account for possibly as one pipe putting a surcharge load on the other, things like that.
Yeah, especially if they're not buried at an equal level, one's higher than the other. You may see that surcharge load. We had somebody else ask about how deep would a pipe need to be before, if it had a building surcharge load, before it would no longer see that building load. And, you know, it's a little bit, it's not quite as straightforward as it seems. So in that instance, or in the instance of doing a dual pipe in a trench, I would just work with your manufacturer. Give them a call. If you have a really small manufacturer in your area, certainly give ACPA a call, and we can help you make sure you're doing a site-specific design and kind of point you in the right direction for that. Another one is, how do we, I think that, Paul, this one's more for you. It's talking about concrete pipe. How do we make sure that a Class 4 concrete pipe miter bend has the same class strength as a Class 4 concrete pipe?
A miter bend? Is that?
Yeah, so they're talking about a special that's been bent.
Like an elbow?
Or, yeah, an elbow. Mm-hmm.
Yeah. Well, I mean, as long as each part of the elbow is a Class 4, it's going to have exactly the same reinforcing as a straight pipe. Now, oftentimes producers may decide to go up a strength class for fittings, special fittings and things like that. So you may have a Class 4 in your main line, but then any kind of a fitting like a bend may actually be a Class 5 pipe. So again, I think that's getting pretty specific, and it may be a very local answer as well. So you'll want to talk to your local pipe producers.
Yeah, great. Thanks, Paul. Another question that came in was DLoad calcs for elliptical pipe. Do you use the round equivalent or the diameter based on installation?
Well, elliptical is primarily based on the span of the elliptical, and you'll see that if you look at the fill height table for an elliptical pipe, that'll be noted, and same with any of the design literature. It's referring to the span, because you're looking at all the vertical loads on the pipe, so it's acting on the full width of the pipe.
Great. So that's all the questions I've seen come in. Again, I've seen a few more people ask how to get the video and those kind of things come through. We will post that to our website, and that link will be sent to you as an attendee of this webinar. So you'll be able to review the recording as well as take a look at the slides in a PDF format. So with that, Paul and Riley, sure appreciate your work on this. You guys have any last comments?
No, it was a pleasure to do it.
Yeah, no, likewise.
All right, well, thanks for your help on this. Again, be watching in October. We'll have another webinar come out with more PDHs available. So thanks again for joining us, and we'll talk to you guys in October.
Thank you.